Right, so now let's take a look at a couple other terms, irreversible and reversible processes, and then we'll kind of use these to explain the remaining couple laws of thermodynamics. So when we talk about a reversible process, really what we're meaning here is a process that can go both in one direction and the opposite direction as well. And the change in the reversible process that is going to occur in such a way that the system and the surroundings can be restored to their original state by exactly reversing whatever that change was, right? So that's how we define a reversible process, one that can go both forward and also reverse. In an irreversible process, that's one that cannot simply be reversed to restore the system and the surroundings to their original states. And there are a couple of these that we mentioned previously that we can revisit here. So we know that heat, just from experience, Q, so that's the abbreviation for heat, moves spontaneously. This is also a spontaneous change, spontaneous process. It goes from hot to cold, right? That's the natural way in which things move, heat in this case. It doesn't go in the opposite direction. It doesn't go from cold back to hot. It doesn't work that way. Right. Similarly, if you have a car, driving a car, and you apply the brakes, well, that converts the mechanical energy, the energy of motion, and then some of that energy is converted into heat, and that's lost. Right. So we have this conversion of um, kinetic energy into heat energy, but it doesn't go back in the reverse direction. Right. So that's an irreversible process. And the other one we mentioned previously is that if you had in a room, uh, you squeeze the cologne or the perfume bottle, and you let some of that molecules come out. Well, the process that happens is an irreversible one in that those molecules, they spread out. Okay, and they don't spontaneously go back into the container, right? So these would be examples of irreversible processes. Now, the other term here that we need to talk a little bit about is something called entropy. Now, without getting too deep into some of the technical aspect of it, because this can be very, very convoluted, but we're just going to sort of give you enough to understand what's going on so we can interpret the other laws of thermodynamics. So when we talk about entropy, really what we're looking at here, entropy, by the way, is abbreviated S, uppercase S. What we are referring to is the degree of randomness or degree of disorder associated with something. So for example, if you can think of, if you have a block of ice, okay, in a container, so there's our ice. And we know that ice is, this is solid, H2O. And from what we know about solids and the solid state is that the particles, okay, are locked in place. They can't move around. And they are in some sort of a crystalline or crystal lattice or repeating pattern. That's why ice looks the way that it does. Now, what happens when that ice melts? Let's say at 30 degrees Celsius. Well, let's just say 20 degrees, which is room temperature. So room temp. Okay, what is going to spontaneously happen at this temperature? Well, the ice is going to melt at that temperature, and it turns into now liquid, H2O. So how are the particles of a liquid different than in a solid? Well, you can pour liquid, first of all, so that means the particles are not locked in place. Okay, they are actually free to move around, to slide past each other. So if you compare the the degree of randomness or disorder associated with a solid versus a liquid. Okay, so in a solid, this is very ordered. The particles are very ordered. Whereas in a liquid, there's more disorder associated with it because the particles are free to start. They're not locked in place. So in other words, if we were to compare the entropy of these two things, we can say that ice has lower entropy. Remember, entropy is the degree of randomness or disorder. So this has lower disorder, meaning that it's very ordered. So lower entropy for the solid state. The liquid state has higher entropy. And in this example, at 20 degrees Celsius, the natural tendency for this is to go from lower entropy to higher entropy, right? We go from an ordered system to a less ordered or a more disordered system. So what's actually happening here is a natural tendency is for entropy to increase. Okay, so there's a tendency for this to happen. Entropy to increase for natural processes. And this is something that you want to keep in mind when we start to, look at different processes. Entropy is a big driving force for whether things are going to happen in the first place under a certain set of conditions. So what we're going to generally see is that for processes that occur without any external input, there is just a natural tendency for these processes to increase the disorder of the universe, and that's actually now ties into our second law of thermodynamics. Yeah, and this can be stated in several different ways, but one way that will kind of explain it here is that the entropy of the universe, remember the universe is the sum of the system, the thing that we're studying and everything else around it, which is the surroundings. So the entropy of the universe increases for any spontaneous process. So the way that we can summarize that now is if the entropy goes up for the universe, that means there's an increase in the entropy, which means that the change, delta S for the universe, okay, what we have at the end compared to what we have at the beginning, that difference there is going to be positive. Okay, whenever you have a positive change, that means you're increasing. So another way of saying that is delta S of the universe is going to be greater than 0 for any spontaneous process. Okay, and you can maybe think of this as in a general sort of way. If remember back to when you were a kid, or when you have kids now, at the beginning of the week, you had them clean their room. It's nice and tidy. And as the week progresses, it gets gradually more disorder. Well, that's sort of a macro analogy to what's happening on a micro scale with atoms, molecules, etc. Right? So we can define the second law of thermodynamics as saying the entropy of the universe increases for any spontaneous process. We can also look at changes in entropy to sort of define other types of processes as well. So for instance, if the delta S of the universe is less than 0, meaning the entropy decreases. So if we do some calculations and we find that the entropy decreases, then that process is actually not spontaneous. So it's non-spontaneous, but the opposite process will be spontaneous, right? So that's looking at it from a slightly different perspective. And what if the change in entropy of the universe is 0? So there's no change in entropy. well, then that process would be known as a reversible process. It can go both forwards and backwards. And we say that that system is at equilibrium and sort of a steady state to think of, one way to think about it. So in a steady, that's what equilibrium means. So both forwards and backwards reactions can happen at the same time. So that's reversible. So looking at entropy, degree of disorder or randomness for a system, we can define a couple different scenarios. Second law says that the entropy of the universe increases for spontaneous processes. The entropy of the universe decreases for non-spontaneous processes, and the entropy of the universe doesn't change if the system of the reversible process that's occurring, right? So this is the second law of thermodynamics. And then the third law is kind of an extension of that. We're not going to get too deep into the third law, but we use it a lot in chemistry, physics, for example. We'll just mention it here, just to kind of complete our discussion. So the third law of thermodynamics says that the entropy of a pure crystalline solid at 0 Kelvin is 0. All right, and again, entropy being a measure of randomness or disorder of a system, it's saying that there is a situation where the disorder is 0, and that happens for a pure solid or crystalline solid at 0 Kelvin. So think about what happens when you decrease the temperature. All right, 0 Kelvin this is absolute 0, by the way. That's the lowest possible temperature. Okay, that corresponds to, if you do the calculation, that corresponds to negative 273 degrees C. Very, very, very cool. So as temperature decreases, what happens to the motion of the particles in a solid? Well, they start to slow down, right? So the molecular motion slows, decreases, and if you decrease the temperature low enough, well, then the molecular motion will just stop altogether. And if it stops altogether and the particles aren't even moving, they're not even vibrating, they're not even rotating, well, then there's no disorder associated with that system. Then we can say that the entropy is 0 in that particular scenario, right? So that's the third law of thermodynamics that defines the entropy of a pure crystalline solid as being 0 at 0 Kelvin.